Bismillahirrahmanirrahim. So we're going to continue from where we left during the last lesson. So we're on question 2, part E. Okay. So for this type of question, I suggest you to always draw so that you can see. Okay. So phenylamine is that treated with propanoyl chloride. So propanoyl chloride is an acyl chloride with 3 carbon. So that's CH3, CH2, and C double bond O. So what happens is that they will undergo an addition elimination reaction. Okay, so this lone pair on the nitrogen will attack the slightly positive carbon. One of the double bonds break, and then it reforms. Okay, and this will result in the release of the chlorine. Otherwise, carbon would have too many bonds around it. I would like to color coordinate this. Okay, and so the product that you will get will be CH3. Nothing changes on the other side of the molecule of your propanoyl chloride. However, this is the new bond being formed. Okay, so NH. So it has to be between the nitrogen and the carbon, and it's only a single bond. Okay, so that's why you have to be careful with your drawing. Okay, at the moment, I'm just going to leave it like that. Now, if you notice on the nitrogen, this nitrogen has 4 bonds. That means one of the bonds have to be broken, and that happens to be the NH bond. Okay, so this is the product that you will form. You have to name the functional group. So the functional group is this one, CONH. Calculate the percentage by mass of the nitrogen. So to calculate the percentage by mass of nitrogen, you have to take the number, the AR of nitrogen, since there's only one nitrogen in this molecule, over the MR of the whole molecule. Okay, and then you times it by 100. So that's how you get percentage. Draw the structural formula of C. Now this is your C, product C, and the structural formula is you must not have any bonds. That means CH3, CH2, or rather H2C, okay, CONH, and then for this one, you can actually draw the benzene ring, or you can write it as C6H5. Okay, so there's no problem with that. Right, moving on to the next question. So you've got a piperine to piperate acid. So if you look at the piperine, there are a few functional groups here. There is alkenes, 2 of them. There is also a CONC, that's it, right? Piperine is an amide and can be broken down as follows. So what happens is that during an amide, you are breaking down the C and bond. Okay, so to start with, you hydrolyze your amide, and then you will form the 2 initial, the 2 of your 2 starting products. Okay, suggest reagents and conditions for this reaction. So you will have a look at the hydrolysis, acid hydrolysis. There are 2 types. The acid hydrolysis is easier compared to the base hydrolysis, because base hydrolysis would require an extra step. Acid hydrolysis of amide. Okay, please look into your notes for this, reagents and conditions. How many stereoisomers are there with the same structural formula as piperate acid? So I'm interested in this structure, piperate acid. Okay, stereoisomers can only be cis trans, in which case you have a C double bond C with different substituents attached to each carbon. Okay, and the other possible stereoisomer is the optical isomer. Cis trans is also called geometric. You're familiar with that. Optical isomer, you need a chiral center. Okay, a chiral center is a carbon with 4 different substituents or 4 different atoms. Okay, so if you look at this structure of the piperid acid, the moment you see a double bond on that carbon, you will not get a chiral center. Okay, so this benzene, it contains alternative single and double bonds. So technically everything here does not have chiral centers. Okay, so we're left with the cis trans, right? But we need to check if the cis trans, there is a double bond, but do they have a cis trans? Okay, so if I draw it out, if we look at the first cis trans, this, technically there should be a hydrogen there, okay? And this would be a carbon. This would be a CH, okay? So if you look at each carbon here, let's just draw that out. There should be a carbon here, okay? If you look at the carbon on one side of the double bond, it is attached to hydrogen and it is attached to a carbon that is a benzene ring and another cyclic alkane, cycloalkane. Okay, so these two things are definitely different. Likewise, for this carbon, which is the other carbon on the double bond, is attached to a hydrogen and a CH and this whole thing. Okay, so you can imagine that these two components are very different. Okay, so yes, you can have a cis trans on this first double bond. Okay, on the second double bond, we need to check as well. So I'm going to just erase everything so that our focus is on the second double bond. So that's a carbon. This is a hydrogen. This is a CH. This carbon has a hydrogen that has been erased, that has been omitted because of the skeletal formula. And the other side is attached to a COOH. So you can see that this carbon has a hydrogen and a CH. Okay, so these two are definitely different. On the other side of the carbon, one of the bonds is attached to hydrogen and the other bond is attached to a COOH. So these two things are definitely different. Therefore, you can have a cis trans. Okay, right. What's the question? How many stereoisomers? Okay, so stereoisomers, first we have to decide what do we have currently at the moment here. Okay, so I'm just going to draw it again. Okay, now usually when you want to name your isomers cis trans, you have to look at the heavier group. Okay, the heavier group, which is, or in this case, it's simpler to look at the hydrogen. Okay, if you look at the hydrogen, on the first, we are going to focus on this double bond first. Okay, the first double bond. So look at your hydrogen. They are across to each other. Okay, they're not next to each other. So in this case, this is called a trans arrangement. For the second double bond, same case. Look at the carbon hydrogen. They're again in the opposite position. Therefore, this is a trans-trans. Okay. So if you think about all the possibilities that you can get out of this isomer, you can get a trans-trans. You can get a cis-cis. That's the easiest one. You can get a cis-trans. And you can also get a trans-cis. That is all the possible combinations that you can get. Okay, so in total you have 4. Draw the skeletal structure of a stereoisomer of piperid acid different to the one shown above. So you cannot draw a trans-trans anymore. okay, because that's already given in the question. Now, I'd like to try drawing cis. Okay, so how do we draw cis? We make sure the rest of the molecules are the same. Okay, so we're dealing with the first double bond now. Okay, so I will now have to bring this group to the bottom. Okay, so let's see. So now I have this. So that's my hydrogen that you cannot see. And then my COOH also needs to be cis. Oh, it says skeletal, yeah. Okay, I'll just draw out the hydrogen first. So you can see how they are cis, but later on you need to erase them because they want you to draw the skeletal formula. Okay, so if you look at this, priority group. So the priority group is on the same side. Therefore, this is cis. Okay, and then for the other double bond, which I'm going to use a different color highlighter, that's the bond, that's the double bond, and that's the bond for the priority group. So you can see that they are again on the same side of the double bond. Okay, so this is how you draw a cis isomer of piperidonic acid. Okay, you can try with cis trans or trans cis. Cis trans would mean this is cis, the other one is trans. Okay, so the opposite is also true. This is trans, this is cis, and yes, these two will give you different molecules. Okay, they're isomers. They have the same MR but different. Okay. Next is because it must be skeletal, so you have to erase all your hydrogen bond. Oh, okay. Okay, your carbon hydrogen bond must be omitted. Next, let me just copy that. Copy. Great. Okay. When piperid acid is treated with an excess potassium manganate, so hot concentrated acidified potassium manganate is your AS syllabus. Okay, so oops, sorry. We want to look at piperid acid. If I just use this diagram again, so then I don't have to redraw it. Okay, so hot acidified potassium manganate means you are cutting the double bond here, completely breaking the double bond. Okay, so when you break the double bond, you will get two things, but this one is a little bit more complicated. Okay, I'll draw it here, so it's relatively easy for us to see. To know the product of the strong oxidation of alkene, okay, so if you want to refer this to your notes, this is under strong oxidation of alkene. Okay, so to know the products, you need to know what is attached on the carbon. Okay, so again, I'm going to redraw this. There is a hydrogen attached there. There is also a hydrogen attached there. Okay. Sorry, excuse me. So when you break the double bond completely, this side will give you this structure. The carboxylic acid product. Okay, the other side, I'll use a different color so you can see. Again, that carbon is attached to another carbon and attached to a hydrogen, so you will get this product. Okay, you can either draw out the structure. What did they say? Suggest structure. Okay, so you can draw out the structure, or you can write down the structural formula. For me, it's easier to draw out the structure so you can see. Okay, so please refer back to your AS stuff, which is strong oxidation of alkene. Next one, writing the expression for Kw. This is your A2 stuff, but in the earlier topic, H plus, the concentration of H plus times by the concentration of OH minus. Okay, calculation. You are to use Kw, and then given the concentration of sodium hydroxide, find the pH. So sodium hydroxide is a strong base. So whatever you started with, initial, 0.150 mole per dm cube, in the end, you will, all of it will be ionized, okay, or dissociated. That's why you get 0.150 of sodium ions and 0.150 mole per dm cube of hydroxide ions, okay? So it's a 1-to-1. It's not like 0.150 divided by 2, okay? You may say, but what if I add 0.150 plus 0.150 of each ions, then I should get 0.30, but my starting material is 0.150. Now, that's not how it works. We know that in the chemical equation, we follow the mole ratio, okay? Right, so here, you already know the concentration of the hydroxide, okay? So if we use the Kw again, then you know the concentration of the hydroxide. Kw is a constant, okay? And another thing that you need to know is that pH is equals to negative log of H plus, okay? If you find the Kw constant in the data booklet, it should be 1 times 10 to the power of minus 14. You know concentration of hydroxide ion, which is 0.150. You can find concentration of H plus. And then from the concentration of H plus, you find the pH. Okay, so that is quite straightforward. The next question, a solution of piperidine. Now, the moment you see a nitrogen attached to what looks like an alkyl group or another carbon, then that nitrogen is most likely going to act as a base. Okay, if it has a lone pair, then it is going to act as a base, right? So the pH of a piperidine is 11.9, but the pH of a base would be somewhat higher, okay, as you know, because sodium hydroxide is a strong base, piperidine is a weak base, okay? So why does this answer differ from your answer in C part 2, okay? So another way of saying that piperidine is a weak base, we say that piperidine is only partially ionized or dissociated. So that's another way of saying that piperidine is a weak acid, okay? How would you expect the basicity of the piperidine compared to that of ammonia? So both piperidine and ammonia are bases. They are organic bases, therefore you would imagine that both of them are weak acid, okay? Weak base, sorry, my bad. Now, in ammonia, you've got 3 hydrogen bonds attached around it. Okay, no effect. In piperidine, you have 2 CH2 group, which looks like an alkyl group. So by now, you should already know that an alkyl group is an electron donating group, okay? When it comes to basicity, we want to talk about how available is this lone pair to attract your H plus, okay? If your lone pair is very available, then we say that it is more basic, okay? If your lone pair is less available or less attractive to the H plus, we say it is less basic, okay? So now, imagine this. You've got a lone pair on the nitrogen. Now, the lone pair of electrons is already like negative charge. You don't see it, but electrons have negative charge. Now, the CH2, the two CH2 groups attached to that nitrogen is pushing more electron density into that nitrogen. So this lone pair of electrons becomes more negative. If it is more negative, that means the attraction to the H plus gets stronger, okay? So that means this lone pair of nitrogen in the piperidine is more available, more attractive to the H plus, therefore it's more basic, okay? So piperidine is a strong, no, don't use the word stronger because both of them are still weak, but piperidine is more basic than ammonia because of the electron donating group CH2. Okay, right. Next, what is the Bronsted-Lowry definition of an acid? Now, there are a few ways of defining acid. You can choose the Bronsted-Lowry theory, you can choose the Lewis theory, but here they specifically asks about Bronsted-Lowry theory, and Bronsted-Lowry mentions about H plus. Okay, so you have to define acid as a H plus donor, base as a H plus acceptor. Okay, Lewis acid, however, we'll talk about the lone pair, right? If you have a look at this, in this case, acid is a lone pair acceptor, but that's the definition based on Lewis theory, and we don't want to talk about Lewis theory. Okay, part B. Draw the structure of the ionic form of glycine. Now, when you want to draw amino acid, I always like to start with the central carbon. Okay, my hydrogen always goes up. My R group will be at the bottom, which I will worry about that later on. And then I've got an acid group, and the other side is my amine. Okay, so an amino, maybe I should change color, an amine group, and then there's the acid group, which is your carboxylic acid, and then your R group. Okay, so in this case, your R, they want you to draw glycine. Okay, if you look at your data booklet, glycine will have its, let me check, R group as a hydrogen. Okay, what's that? Let be. Oh, all amino acids are soluble in water. Since they can form hydrogen bonds with water molecule, they can also exist as deuterions. Draw diagrams to show how carboxylic acid and amino groups of adenine can form hydrogen bonds. Okay, so I missed that question. So let's try to draw the what is it again? Hydrogen bond. Okay. So first one, the easiest one is the amino group because it has a lone pair. So when you have water, obviously this nitrogen is already the negative part. So it's the positive part of water that attracts the lone pair. Okay, so it has to have a delta plus, delta minus, the nitrogen, and then you can label that as a hydrogen bond. Okay, with this can also have delta plus. Nitrogen will be delta minus. Okay, with carboxylic acid, same thing. You can draw water the H plus of what, the hydrogen, which is the one with a slightly positive charge, will be attracted to the negative charge of lone pair of electrons. If you want to draw another hydrogen bond, you can draw it here, but you have to draw it as COO minus, okay? Like this, C double bond O, O minus, okay? And then again, sorry. You can leave it as hydrogen, but you will draw a dipole. Oxygen will be more electronegative, therefore delta minus. Hydrogen will be less electronegative, therefore delta plus. And then of course the delta plus, the slightly positive hydrogen, will be attracted to the lone pair on oxygen of your H2O, okay? This will be delta plus, delta minus, delta plus. So that's how you draw your hydrogen bond. You might want to label your hydrogen bond as well. Some examiner would appreciate if you could label them, okay? Back to the zwitter ionic form of glycine, okay? The R group in a glycine is hydrogen. So I will change that R into a hydrogen and maybe use a different color, purple, okay? So that's my hydrogen, right? But however, that's not answering the question yet, because the question wants you to draw Zwitter ionic. Zwitter ionic means you have two charged in this molecule. So as a matter of fact, proton transfer will happen here. Okay, so what happens? The hydrogen from the carboxylic acid, the green hydrogen from the carboxylic acid, will be transferred to the nitrogen of the amine group. So when we lose this hydrogen, the COOH becomes COO minus, and the NH2 now becomes NH3 plus. Okay, so this is how a Zwitter ion looks like. Now, even though that they are charged, positive and negative, they will cancel each other out, and overall, the molecule is neutral. Okay, the number of atoms and the MR is also neutral because you have not lost or gained any H plus. So what you did is what we call an internal transfer. Okay, you transfer from the acid group to the amine group. So no change in number of atoms or whatsoever. Okay, next is the amino acid can be formed by the reaction of CH3Cl, CHL. Okay, so I'm just going to draw this structure first, and then hopefully you can see CH3, CH, Cl, and COOH. Okay, plus ammonia, maybe a different color, NH3. Okay, now I hope this rings a bell. If you look at the chloropropanoic acid, okay, there are two functional groups here. The carboxylic acid, which is of no use in this reaction, but I will tell you that the halogenoalkane CCl is the reactive part of the mechanism, okay? So carbon and chlorine has very different electronegative value, with chlorine being more electronegative, therefore it will develop a slightly a delta minus, okay, slightly negative charge, and that makes your carbon has a slight positive charge, okay? So this reaction is ammonia in this case is acting as a nucleophile, therefore nucleophilic substitution. Okay, so when this lone pair on the nitrogen attacks the slightly positive carbon, the carbon-chlorine bond will break, okay? You may ask, why is it carbon-chlorine? Why is it not the carbon that is attached to the COOH, or the carbon-hydrogen bond, or the carbon attached to a methyl group? Now, this is because the carbon-chlorine bond is the weakest, okay? Therefore, it tends to break. The carbon chlorine bond tends to break. So this is called the nucleophilic substitution reaction. I want you to go back to your AS notes and look at the reaction of SN2. Okay, it should be similar. Now if you don't have your notes, then that would be a problem to you. You should have your notes with you. Okay, right. I think we still have time. Amino acids can form different ions at different pH values. Suggest the structures of amino acids at their respective value. Now we've ignored the value first for now. We're going to draw lysine. Okay, so as usual, I have my NH2, and then I have my acid, I have my hydrogen, and lysine, if I look at the data booklet, okay, so no one is expecting you to memorize. Lysine has an R group of CH2 4 NH2. So this is lysine. Okay. Right, so they want you to draw lysine at pH 1. pH 1 means you have a lot of acid. Okay, so a lot of H plus. So you have to think about this incoming H plus who are going to pick them up. Okay, so first of all, I hope the obvious one you can see is that nitrogen in your amine group. It is a base, therefore it can pick up your H plus ions, but that would mean that the nitrogen would develop a positive charge as well. Okay, but do not forget the NH2 in the R group, this one, is also a base because it has a lone pair. Okay, so same thing, another H plus will be attached to the nitrogen. That makes your nitrogen have a charge of positive. Okay, so this is the form of lysine at pH 1. Overall, this lysine at pH 1, it has a charge of +2. I hope you can see that. Okay. Okay, next one is aspartic acid. Same thing. Focus on the structure of the amino acid first. You have a carbon, you have a hydrogen, you have an NH2, you have a COOH. So both amine and carboxylic must be there. And the R group for an aspartic acid, as referred to your data booklet, is CH2 COOH. Okay, so now this time we're in a region of pH 14. That means we have hydroxide ions more than H plus ions, or in a way we are losing our H plus ion. Okay, so what happens is that our hydroxide ions will pick up the H from our acid. Okay, because hydroxide ion is a base, it will react with an acid. So the only part of an acid here is the COOH, okay? When we lose H plus, we will be left with COO minus for the carboxylic acid group, okay? Not to forget, the R group also have a COOH, which is an acidic part, okay? So this acid, the H plus in COOH will be taken away by the hydroxide ion, therefore it now becomes COO minus. Okay, so overall for aspartic acid, the charge for aspartic acid at a high pH of pH 14 is -2 or 2 minus. I hope that's quite clear to you. Okay, why aspartic acid would have a charge of +2 at higher pH. Okay. How many different dipeptides is it possible to synthesize, each containing 2 of 3 amino acids? Alanine, serine, and lysine. So I'll just write down in. So again, make it a habit to draw your amino acid. A is alanine. Alanine has an R group of CH3. Okay. Should be NH2. Okay. S, using a different color, would be again same thing. There is wrong. Can anyone spot what my mistake is there? Because my carbon is attached to many things. There should be another carbon. Sorry, my bad. Okay, so carbon, nitrogen. So nitrogen, 2 hydrogen, COOH, and then this is CH3. Okay, for serine, same thing. Start with the carbon in the center, COH and NH2. Okay. This one would be H. Serine, the R group would be CH2OH. Okay. And for lysine, same thing. Carbon with an amine with carboxylic acid with hydrogen on top, and at the bottom, lysine is CH2, 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 1, 2, 3, 4, CH2, and H. Okay, so you are asked to draw out 2 out of 3 with the maximum number of combination possible. Okay, so I will tell you that there are 6 possible combinations, and these 6 are AS, AL, SL, SA, LA, and LS. Okay, you may think that, oh, isn't SL and LS the same? Well, nope, because, okay, let's take AS and SA for an example. AS and SA. Now, for first possible option, AS is I use the acid of my A and the amine of my S. Okay, SA means I use the acid of my base and the base of my A, okay, which is alanine. Okay, so AS and SA is not the same, AL and LA is not the same, so is SL and LS. Okay, write the structural formula incorporating serine and alanine. So you are given a choice here. You can choose the acid of serine with the base of lysine, or the base of serine with the acid of lysine. Okay, so any combination is possible as long as it's acid and base, not acid or base combination. Okay, so just choose one. Okay, if we just look at S and L, I take that so that I don't have to withdraw it again. Copy. Okay. Right. In this case, I have already arranged my serine and lysine so that the acid is in contact with the base. Okay, so what happens during addition elimination, we will lose the OH from the acid and the hydrogen from the base. Okay, you lose water, and the bond that you are forming is a peptide bond. Okay, so be careful that when you draw, when you draw the C single bond end, you only have 1 hydrogen and you only have 3 bonds around the nitrogen. Okay, so I will leave you to do that. So that is all for today. Okay, so sorry if I'm going too fast, but you can always pause the video. Okay, right? So that's all. Assalamu alaikum, and thank you everyone.